My name is Fahad Islam, and in this talk, I am talking about a provably constant time planning and replanning approach for real-time grasping objects off a conveyor belt. Robots are often deployed at conveyor belts in warehouse and manufacturing environments to perform fast pick-and-place operations under strict time constraints. This requires motion planning to be fast and reliable. When the incoming objects are seen from a distance, the perception estimates are often noisy. For fast-moving conveyors, the robot cannot wait for a perfect estimate before it starts execution. To reach the object in time, it must start moving early on, relying on the initial estimate, and then adjust its motion on the fly in real time as it gets better estimates from perception. This enforces a requirement that the motion plan must be generated in constant time, that is, within a fixed time bound. Here is the full system in running. The robot has to pick up a sugar box from the conveyor belt, which moves at a speed of 20 centimeters per second, and a fixed bound of 0.2 seconds is set for the motion planner. To the right is shown the camera view of the robot that is used for perception. The robot gets the first pose estimate at this point and generates the initial motion plan to pick up the object. As it starts executing this plan, it gets an improved estimate from perception and generates a new plan. It then receives a third estimate with no further correction and thus continues to execute the previous plan until it successfully picks up the sugar box. The highlight of our approach is that we leverage pre-processing to generate a database of paths that can be used at runtime in such a way that provides constant time planning and replanning guarantees. And to the best of our knowledge, none of the existing algorithms provide such guarantee. Now let's look at the problem setup. As inputs to the system, we specify a goal region for the motion planner, which comprises of all possible pose estimates of the object when the object is first seen by the robot. We also specify a fixed start or home state, which corresponds to the drop-off location of the robot. And we set the time bound for the motion planner. At query time, given the current state of the robot and a goal pose, the motion planner is tasked with generating a trajectory that grasps the object. To understand the complexity of the problem, let's take a look at a strawman approach. Here we show a 2D illustration of the problem setup that I just described. We have a goal region G full and a home state S home, and the planner might have to replan from any intermediate state as well. Now the strawman algorithm in the pre-processing phase would just pre-compute and store paths from all initial states of the robot to all the states in G full. To break it down, from S home at time step T0, it requires computing n paths where n is the number of goals in G full. These paths generate n states at time step T1 from which it might have to replan. So, at time step T1, it needs to compute n additional paths from each of the n states, resulting in order of n squared paths. And so it can be seen that the computational complexity is exponential in the total number of time steps, that is t. Now we can store these paths in a lookup table that can be used at query time to answer any query. This strawman algorithm, however, is clearly intractable due to its memory and computational requirements. To compress the number of paths that we need to pre-compute, we make use of an experience space planner P. P can use experiences to speed up planning for similar queries. In the example shown on the right, P can use an experience by 1 to plan to all the goals in the set of goals G1 within T-bound time. So instead of having to store paths for all the goals in G1, we only need to store a single experience by 1. Our key idea is to compute for each state S a set of experiences that ensure that P can reach any goal in the full goal region in T-bound time. And here is a visualization of the experiences generated for the home state. Now to replan from any intermediate state, our algorithm iterates through all the states on these experiences and adds additional experiences so that it can replan from these states as well in T-bound time. And this has to be done recursively since adding new experiences generate new states that need to be processed. We report the success rate of our approach of continuous replanning and compare against single-shot planning approaches, one that relies on the initial inaccurate estimate and the other that waits for the accurate estimate, and we achieve a much higher success rate for the conveyor pickup task. To conclude, through this work, we advocate that constant time motion planning is vital for the robots working at conveyor belts and for potentially other time-critical industrial applications. If you are interested, please reach out and I will be happy to talk more about this work.